In this example, we're coming back to the blocks on a ramp that I worked on with the previous example, but this time we're throwing in an additional hitch of friction. There's going to be a coefficient of friction between this block and the ramp of 0.552. Now, if you haven't used coefficients of friction before, the way they work is, if I want to find the frictional force, I multiply by the coefficient of friction times the normal force, and that gives me the frictional force. We're going to place these two blocks on this ramp, or one on a ramp and then the other one attached by a massless string over a massless pulley to a massive block, and let them go. And they're going to accelerate. Now, based on just looking at their masses and this one being bigger, I assume that they're going to accelerate so that this one goes this way and that this one goes this way. Now, if I'm wrong, then my answer will just be a negative number based on how I'm going to set this up. I get to use different coordinate systems for each block if I want to. So what I'm going to do is I'm going to call this direction positive for this block and down positive for this block. And if we really want to be picky, we could say this is positive y and this is positive x for this block. Because you might remember that I said whenever you have a block on a ramp, the handy trick is to rotate your coordinate system so that positive y is at 90 degrees to the ramp. Be positive y, and in this case I'm going to call this positive x just to make some things easier, mainly because I think the block will go this way and then I think this block will go this way. So I want to get a positive acceleration for both blocks. That's not necessary to set it up that way, but for me at least, I have been dealing with negative numbers probably about 7 years longer than positive numbers. You just think back to elementary school education and when you learned about numbers, and then when you learned about negative numbers. So these are still easier for me to think through. And then I am going to start drawing the forces on my blocks because I know that we're dealing with acceleration, so this is probably a force problem on some level. So the block on the ramp has normal force. And if I'm right about the direction of acceleration, the frictional force will point this way. But again, I could be wrong. As long as I'm on the right axis, x or y, I'll still be able to do the problem. I just might get a negative number if I've chosen the directions incorrectly. And tension from the string and gravity. And then for this block over here, we have gravity. Oh, and now we're going to run into trouble. So I'm going to call this block 1 and this block 2. Otherwise, I'd have FG, and they wouldn't be the same, or not necessarily the same. They don't have to be. And force of tension. Now, remember I told you about the Bob Marley rule. If you have one strain, one tension. So I know that FT is the same on both blocks because it's the same string connecting them. I want to find the acceleration for both blocks, and I'm pretty sure that the block here will accelerate in x, and this one will accelerate in y. So I'm really only worried about the x forces here on this block and the y forces here on this block. So let's go ahead and write that down. Let's have the sum of x forces on block 2, the one on the ramp. And if I just look at my diagram, so in the positive, I'll have a force of tension. And then against that, my frictional force should be an F. And then there will be a component of the gravitational force. So think about it, since I rotated my coordinate system, that means that gravity is no longer just on y. Part of it is pointing in the x direction. So I need to find the x component of that gravitational force. And the x component of that gravitational force should just be Fg. If I look at it, the x component is opposite, so that should be sine 40 degrees. And that will all be equal to the mass of block 2 times its acceleration. And I'm not numbering the acceleration. These two things are attached by a string. And if you watched the video of the 15 train car problem, or did the homework of the 10 train car problem, the whole system is accelerating because it's attached, and then we're not letting the spring stretch or compress. So they will both accelerate at the same rate. Now we need to consider block 1. And for this one, I chose down as positive. Oh, and I made a mistake here. So remember, we're talking about the y forces on block 1, because I'm pretty confident it's accelerating in y. So I will have force of gravity on block 1, positive, and in the negative direction, the force of tension. And that would be equal to the mass of block 1 times the acceleration of the system. Now what I want to do is eliminate one of the variables because I'm looking for the acceleration of the system. And ultimately, we can find the acceleration of the system. We can also find the tension in the string. Those will be the two things we look for here. So I want to eliminate one variable. And I can either get rid of A, or I can get rid of T. For now, I'm going to try to get rid of T. So I'm going to rewrite this equation to say what T is in terms of other things. So force of tension, if I move force of gravity over here, and then multiply through by a negative sign to get rid of that, I get Fg minus M1A. And now I can take this force of tension and substitute it into this equation up here. So let's rewrite this equation. We'll have Fg minus M1A replacing Ft, so Fg minus M1A, and then just continuing along, minus F minus Fg, oh, and I got sloppy with my numbers, 2, sine 40 degrees equals M2A. And now notice that equation does not have tension, and there's only one thing we don't know, acceleration. Now you might think to yourself, well, do we really know the force of friction? We can find that. So remember, force of friction is mu s times my normal force. So if I look at this diagram over here, I need to get the normal force. And this block is not accelerating in y. It's not going to fly up off the ramp. It's not going to fly down through the ramp. We're pretty confident it's just going to move how the string pulls it. So that means I can say that my normal force and my y component of gravity are equal to each other, because I need sum of forces in y to be 0 if it's not accelerating in y. So let's do that. The y component of the gravitational force, that would be adjacent, is Fg cosine 40 degrees. And then my frictional force would be mu s Fg cosine 40 degrees. So I can put that in for my frictional force. Fg minus M1A minus mu s Fg cosine, oh, and sloppy with those numbers again, 40 degrees minus over here Fg2 sine 40 degrees equals M2A. All right, and now I am still looking for acceleration. So let's solve this equation for acceleration. If I move this over here, I'd have M1A plus M2A. Let's write that down. Fg. I'm going to move the M1A over. So S Fg2 cosine 40 degrees, G2 sine 40 degrees equals M1A plus M2A. Now hopefully you recognize that I could factor this and just make it M1 plus M2 times A. And then to solve for A, I just divide by M1 over M2. So this whole thing, A, is going to be equal to Fg minus mu sine 40 degrees sine 40 degrees over M1 plus M2. Now we can start substituting in numbers. So I will just start looking up here. If I need Fg somewhere, got lost on what this is, so let's try to track it back. Now notice how I've laid out my work here. It makes it really easy for me to figure out a mistake. There is no number on this FG, so I need to figure out if it was FG1 or FG2. So let's start going back up. Okay, it came from here, and that looks like I substituted in here. FG, I didn't label it there either, so let's go back up one step. It was FG1. So notice I made a mistake because I was being sloppy, but because I had laid out my work all in a line, doing one thing per line, I can just go back up and say, oh, yep, that should have been FG1, and propagate the change through. All right, so I like to just call little g 10 instead of 9.8 because it makes things easy to multiply. So if I'm looking for FG1, that's the mass of block 1 times little g on Earth, 10. So 4.75 times 10 is just 47.5 newtons. And minus mu f from our problem, that's 0.552. And FG2, same way to find it, mass of block 2 times little g, so that'd be 28.5 newtons, cosine 40 degrees, minus 28.5 newtons, sine 40 degrees, all over mass of block 1 plus mass of block 2, so 4.75 plus 2.85. And I get that that is 7.6 kilograms. And now I just have to grab a calculator and do this all out. Now it's really easy to make a mistake with this much going on. Make sure your calculators are in degrees mode for checking what I do. And when I plugged this into the calculator, I got 2.2 meters per second squared. Now what's left is to find the tension force. Well, luckily, I have an equation for that. I wrote it up here. So this part should be pretty easy. Force of tension equals, by the way, this is my correlation. So back here, force of tension equals Fg1 minus M1A, which is, we already talked about Fg1, 47.5 newtons, minus M1, 4.75 kilograms, times the A of the system, 2.2 meters per second squared. And when I plug all this into my handy dandy calculator, I get that my force of tension is 36 newtons.